So please give it up for Gergely Brautigam.
Thank you. Hello, everyone. It's been quite some time since I saw this many people in the flesh. So I'm a tiny bit, but forgive me for losing my thought from time to time on that. I'll try to pick myself up. OK, so distributed face recognition with Go. So what I'm going to talk about is a pet project of mine. We have an agenda, kinda, sorta. It's not very rigid. Like, we'll see how it goes as I talk about things on here. I'll ask some questions about prior knowledge about stuff. So how deep should I dive into a specific technology or a thing that I'm using? And then a small introduction of who is me, and then the technologies I talk about, what I'm using, and architecture, Kubernetes, distributed systems, and then demo time. And maybe we'll do this one. It depends on how much time is left or how things go. All right, so let's, hands up, who here knows Kubernetes fairly well? All right. Somewhat. All right. gRPC. All right, that's good, good, good. And in regular distributed systems, as in building, maintaining, and so on and so forth. OK, cool, cool. And SQ, we don't care about that. SQ comes later. All right. So, as Matt said, I'm Gergely Brautigam. I work at Weaveworks, no pun intended, and Twitter, GitHub website. All right. So the first question would be, why? Why does this project exist? What am I trying to do even? And the obvious answer is, of course, for the glory of the Sontaran Empire. But actually, this is all done because of learning. So I learn the best when I do something, if I create something. I started this little project of mine 4.5 years ago. I knew very little about Kubernetes. I just read the book Kubernetes Up and Running. And I basically tried to put something together, and put something together that actually does something interesting. I also dabbled in Go, so I tried to use Go as much as I can in various projects. I have not worked with Go professionally yet, so this was basically a side project I was doing and learning the technologies, learning Kubernetes, learning all of its moving parts, how they fit together, service discovery, and so on and so forth. So this is how this project came to be, for fun and profit. All right, so technologies. First one is gRPC. The order is kind of, but let's talk about gRPC. So I'm using gRPC and protobuf between two of the services to communicate. And I'm using gRPC because of a couple of things. It has a strict contract. It's very easy to use. You have type safety, discoverability. And what does this mean? The strict contract means that it becomes more difficult to break a contract with your clients than if you would have a JSON API, because it comes very apparent that you broke something, especially, I'll talk about that later today, later in this slide, especially if you use something like buff build, which now has linters and breaking detection in its generator. So it can basically generate you code, and it can check your protobuf descriptor. file if you have any breaking changes from one change to another. So for example, you change a version of one of the parameters, or you change the ordering of the parameters, or things like that. These are all breaking changes, and you are immediately notified of that because of your linters and actions. Whereas compared to a JSON API, it's kind of really easy, unless, of course, you have like proper integration tests and unit tests, which you all should have. It's kind of easy to just change a character from message to message, right? Just leave an E out, and suddenly nothing works anymore. And you have like, if you're dyslexic like me, you stare at something for an hour, and you can't see what is wrong. And then you compare it like character by character and find that, oh yeah, an E is missing. And easy to use. It's very easy to use. For example, at Weaveworks, we refactored one of our services from a JSON API into a gRPC-based API. And we literally could throw out half of the code that we wrote just to like parse JSON, have test data, test loaded data that we have to like integration test if we didn't break something. We had a bunch of canned responses, and so on and so forth, and the HTTP handler mocking, and everything that comes with that. We could throw the whole thing out and just call code, and just unit test code with mocks, of course, but those were generated. So we didn't have to deal with that. And the fakes helped us to fine control every aspect of it without having to deal with return error codes and headers and whatnot. So it's really cool. And then discoverability, what do I mean by that is that unless you have like Swagger documentation on your JSON API, like proper Swagger documentation, and you have something like Postman or something that can test these these things, or Swagger itself lets you use sample responses and can generate. It's really cool. But if you do not have Swagger, then it's really difficult to go and discover what your API does, or what your API can do, or what kind of endpoints even do you have, or what services do you provide, or what's even happening there. So with gRPC, kind of like Swagger, you have your service description, your protobuf description, and it tells you all the things you need to know, all the services that you have that can be called, all the return types and return values. And that's what you get from type safety as well. You will always, your client, the client that you generate will always know what to call how and what that thing will return. So yeah, use cases. And buff build is a relatively new thing that came along, which can reuse protobuf modules. What that means is that you define a service like a general API or a service that is that is crucial to your application. And instead of pulling down that proto file into all of your services and having to implement it, or clients and having to implement it, protobuf buff build provides a registry or online registry, almost like GitHub, for your protobuf files. So you can basically, in extendable modules, depend on that file through buff build. So you would, something like Google's annotations API that is needed for a gRPC gateway, you just say, yeah, pull that down from buff build and say buff generate, and it will gather all that dependency down and build it for you. So you don't have to download the annotation protocol definition. You don't have to download anything. It will take care of that for you. So that's pretty cool, and you get that for free with gRPC and protobuf definitions. So drawbacks. Obviously, it's not a one-size-fits-all. There are always drawbacks, and in this case, it's the rigid structure. which means that it's a good thing, bad thing kind of situation. With the type safety and strict contract comes a rigid structure that is really difficult to change once it's been established and easily breaks things. Having to provide an SDK, what I mean by that is, for example, if you build something like a plugin type of architecture for your thing that uses gRPC to communicate between your main application and the plugin, for example, things like HashiCorp's Go plugin library, then it's true that gRPC is language agnostic, but you will have to define or provide an SDK for your clients in all languages that you would like to provide for or handle because of how because you would like to make it easier on them to use your stuff. So you'll have to write an SDK to things like get customer or get whatever. And more overhead to implement from the client side. This means that, for example, for JSON APIs in interpreted languages, you just say, like, put the whole thing into a dictionary and then just call whatever .customer, and Python will surely tell you if that exists or not, or JavaScript or whatever. And that's a pretty good thing. It's kind of lazy. You can't do that with type things. All right, so that was kind of gRPC. So let's go for Kubernetes. There are a lot of things to talk about when Kubernetes is in play. I will try to limit this and not bore everyone with too much details. I'll try to say in what regard is this application using Kubernetes. For example, there are deployments and stateful sets in this thing. Deployments via stateful sets. Stateful sets provide statefulness, kind of in the name, and deployments do not. And we have some network policies, as we talked about this earlier in one of the talks. Network policies can restrict communication between services. So, for example, you can say that your database will be only able to talk to these certain locator selector labels. So, like only with the application, and that's pretty easy to set up. That's like a very cheap win. A network policy is like this many, it's this long. It's still YAML, but still, it's very easy to set up, and people tend to forget about network policies. I mean, it's nice if you have RBAC installed and compiled everywhere, set up everywhere, but network policies still give you like a very nice, rigid restriction of networking. And then the main thing I'm using is service discovery between services. So this is like we will deploy like 5 services or so, and these services will need to be talking to each other to configured endpoints, and these configured endpoints will come from the service that Kubernetes generates, the service names. Persistent volumes and claims. One of these services uses storage, and this is I'm lying. This is not configured to persistent volumes and claims because of a bug because of a bug in kind, the thing I'm using to test. But eventually should be, and in production should be, used with persistent volumes and claims. They basically, you claim a slice of storage, and then you define a slice of storage, and then services or applications can claim storage, some amount of storage from this pile, basically, and say, yeah, this 5 GB out of 100 is mine, this 5 GB out of 100 is yours, and so on and so forth. That's how you define it. And this is cool because they remain and remain attached to a service. And if your service restarts, the same service, the same pod, will claim the same volume with the same data. So this is how persistence works. Resource limits, very important, often neglected. Again, when I first started with Kubernetes, I also neglected it and completely nuked my DigitalOcean cluster with a single cron job because it was firing over and over again, and there was no regard in like how many times it can run, how much resources it eats. So the cron job, it remained running, and it fired, and it slowly like ate up all of the resources, and suddenly I wake up and nothing runs. And yeah, that was fun. I tried to not nuke the cluster and get everything back up, but it's not always that easy. Load balancing is important. There are a bunch of other things in Kubernetes land, which I'm not going to cover. Load balancing, certificate management, and let's encrypt. Sounds cool. Not gonna set it up. And then readiness and liveness probes. These are also very important to see and know when your application is actually running. I did not set that one up either. All right, NSQ. So NSQ is a real-time distributed messaging message processor at scale. There's a bit of a typo there. Basically a queue. It's very cool, written in Go, been active for a long time, actually released recently a more a lively version, and they redesigned the whole distributed setup, which is really cool. And it still works, which I was surprised by. There are a number of alternatives right now, like KubeMQ, but NSQ is still like the best queue managing system. It's distributed with a thing called NSQD and NSQ lookupd. Basically, you run NSQ as a stateful set, and you run NSQ lookupd as a stateful set, and your consumers and producers are completely decoupled from each other. They don't know anything about each other. Things send things to NSQD, and NSQD then talks, NSQ lookupd then knows about all of the little NSQDs running, and your consumer talks to NSQD and basically gets the data which is on the queue out of NSQ lookupd, which will propagate down to the rest of the things. It's really cool, very easy to set up. And then Go. How is Go helping in all of this? It's really fast, I like it. It's really easy to work with. Easy on the concurrency side, really, when I was learning, I really like channels and the whole coroutine experience. And it's easy to write and begin. When I first wrote this project, like four and a half years ago, more than 4 years ago, I knew very little. I did contribute to Go at some point, but still it surprised me how easy it was to just write four or five services that talk over the network in a distributed manner. It's really cool. And of course, that's why you are all here. We all like Go. And there's a circuit breaker as well, which I will talk about in a bit. And then the face recognition part. I'm really sorry, but it's a Python library. How does that work? And why is it a Python library? At the time where I began this, there's a thing called GoCV. Maybe a couple of you heard about it. It's trying to do all the OpenCV stuff, but from a Go, it gives Go bindings basically to all the OpenCV stuff. And but it doesn't do face recognition. It does face detection. So, and it still doesn't, and at that time it certainly did not. There are a couple of alternatives out there that are written in Go that do C bindings to dlib, which is the face recognition part. But they are either abandoned or very immature, or insanely hard to set up and use, to be honest. Whereas in the Python library is a gRPC call away, which is cool. And so it has a number of awesome capabilities in it as well, like a real-time face recognition, so like a camera. And it can detect multiple faces and return multiple results for all of those faces, and recognize faces on a Raspberry Pi camera, and many more. All right, so let's talk a bit about the architecture. This is basically it. So, what's happening here? So you have your camera set up, which is a really bad acronym for curl. And that takes an image and sends it to a receiver. Obviously, this is like needlessly complicated to the point of being insane, right? But again, the reason was learning. So I threw in most of the things in there. So gets an image from a camera, either live or a picture, doesn't matter. Sends it to a receiver. The receiver sends it along on the queue, but also saves it into a database. So we will talk about this later in a bit. There are 2 sync points in this whole application. I'll mention them in a bit when we talk about the data flow. Sends it to the consumer. The consumer will consume it and send it to the so he's the processor, actually, the image processor. Send it to the face recognition service, which will identify the service and send it back to the consumer who it is, and that will then save it in the, update the record, basically, for that image. So let's talk about the data flow for that. Okay, so this is the basic architecture. And we have the database and the storage. And the database is the main, the main sync point. So in every distributed system, you need a sync point. Unless you are fully like stateless, or you don't need any of that stuff, then of course you don't. But, well, you still need network governance and load balancing and stuff like that, but you don't need to sync the state. But if you have state, you have to sync it somewhere at some point, be it immediately consistent but not very performant, or eventually consistent, and so on and so forth. So my sync point is a MySQL database. It's not sharded. It's really difficult to shard databases. So for the sake of this project, it is not sharded. But basically, you make it more robust by separating the database or sharding it, and then setting up the necessary syncing between the shards. We have the receiver, the sender. I forgot the name from that one. He's the receiver, basically receives the image, details about the image. And we have the NSQ, and we have the image processor and the face recognition service. So what does the storage do? The storage stores the images. It stores 2 types of images. It stores known people and unknown people. The known people are all the people that you either already recognized, or you labeled them yourself, or you sent it through like a machine learning algorithm that identifies them for you from another record. But either way, you need a storage of people's faces and then link them somehow to people that you know. Since this came out as a pet project, and my whole use case, I'll talk about the use case after this, is very simple. I know like 3 people or so, including my wife and child. And so I wasn't too much concerned about that filling up too soon. And then you need unknown people. So the unknown people will be filled up with the images that come from the camera, wherever that is. Unknown people's images are loaded into the Python library, and the library will do its magic. So what's happening here? The first one is, in comes a new image. I forgot an arrow there because the new image is also in the unknown people storage. So in comes a new image. This is /temp/unknown01. And we send that off into the database. We create a record and get back an ID for that record. I use the database to generate IDs instead of using something like a UUID. I'm also using transactions all over the place to ensure that there's no collision. And then what happens is, and the receiver also puts the ID of the generated record onto the queue. The queue will then be consumed by the image processor, and it gets an ID. Why aren't we just sending the path if eventually the path is the only thing that's important? Is because the path is technically not unique because it can be retried if it fails later on. I forgot to draw the redeemer somewhere here because it's a cron job that picks up failed images and puts them back onto the queue. But the ID is not. And it needs to get the image anyways because this will be the one updating the image with the person that was identified. So it gets the ID, gets back the image, also with transactions, and sends it off to the face recognition service. What does it send to the face recognition service? It sends the path, because the face recognition service doesn't care about the DB at all. It cares about the images, and the image is the unknown 01. So what is this? This guy is a circuit breaker. So the circuit breaker, for those of you who don't necessarily know, it will trip in case there is too much load on the backend service. So the backend service just replies with an invalid message, like a 500 or something, and it's down. Then the circuit breaker will say, let's not put more pressure on the backend. Stop hitting it with requests. Somebody also said DDoSing it. Basically, the circuit breaker will prevent any further actions once it's tripped. It also has a timeout. So if it times out, it will try a ping, which is just like a health check. Since we are using gRPC, it's just the gRPC health endpoint. So it will call that health endpoint that, are you alive? And if it's alive, then it will allow more data to be thrown at the service. Failed images are not retried at that point. Failed images are just set as failed and will later be retried when they are back on the queue. Because we don't need immediate recognition for those. Then what happens? So face recognition service does its magic, accesses the storage, gets all the known people and unknown people, and replies back to the image receiver with the result, which should be a name associated with the known people. So known people will contain, like for example, it can contain many images per person. So like for me, for example, there are like 5 images which are following rule of being person name and 01 or 02, 03, 04. And it will basically say, okay, the identified image is Gergely 01. And we don't care about the rest because we already know it's Gergely who was identified because we know that all those images are belonging to me, belong to this person. And yeah, that's what it gets back. And the image processor then saves the result, saves it back into the database, and your person has been identified. So that's about it for the data flow. So let's talk about the distributed nature. So how distributed was this? A couple of services here and there. There are a couple of pain points. For example, the database. So let's talk about how each of these could be scaled, or what happens when you scale these. So if you scale the receiver, for example, that's fine. With the transactions protecting the database, you could put a load balancer in front of the service of the receiver, which will just load balance all the requests between the individual receivers. You can scale the database. For example, it's very easy to scale nowadays with Aurora or GCP, or there's a thing called something stack. I wrote it down, which provide now very cool, very easy, on-demand, scalable databases. So you don't have to actually deal with that stuff. Sorry. The face recognition part is a bit trickier because potentially if you have like a million or 2 million images, you don't want to load all of those images right always up. So what you could do, technically, is come up with a way of slicing all the known people into stacked up parts, and then have the Python service identify or claim one of those slices based on some unique identifier per service. And so you say one of these slices is claimed by 1, the other one by 2, and so on and so forth. So you could chop up a million or 2 million images into a certain set of slices. So the known people obviously doesn't get too large, right? And at some point you hit a limit. So you're probably fine in scaling that. And then NSQ just scales itself. That's why I really love it. It scales itself with the NSQD and NSQ lookup. The image processor, again, is really easy to scale. It's using transactions, put a load balancer in front of the service's face recognition, and everything just sort of works. Obviously, that's like famous last words, but trust in the system. Yeah. Okay, so what are actually the use cases here? Like, why am I even doing this? So one of the use cases is a meeting announcer. You could hook this up into a camera in front of your house, right? And hook it up into a Google Calendar, hook it up with known people, and associate those known people with Google addresses or Google people or whatever. And then when somebody steps in front of the camera, you have them identified and send a push notification to Alexa saying, hello, my 11 o'clock is here. Please open the door, or something like that. Another one is dog belly rubbing appointment. When your dog comes along and says, yeah, hi, Maya, I'm here for the 11 belly rubbing. And cat feeding time, obviously, is a very good one. When they step in front of a camera, which is set up for a dispenser, detects their face or detects the cat object. Yeah, it can also detect cats. It's really cool. And dispenses food. Mood tracker, this one was an idea of a coworker of mine. You could basically, when you leave the house, detect your face, and when you come back and see how your mood changed in between being out and coming back. So obviously this was a very, very convoluted architecture because, like I said, for learning purposes, a very Simple one would be just hooking up a Raspberry Pi to a camera and calling the Python service and pushing something to Alexa or whatever, what have you, that says something. So this would be, of course, a lot simpler, but nothing learned, nothing gained. All right, yeah, real purpose, show off of technology, power of Go, learning the architecture, learning Kubernetes. All right, so let's show this thing actually. Oh, I did not start the thingy. Okay. Hope the network is okay. I wanted to start this before I begin the talk, but forgot. So it sets up how does this work? You can see that it sets up a kind cluster. Kind, if you don't know that one, that is a very cool tool to test Kubernetes locally. I think it's a lot easier and nicer to use than Minikube. Kind has this cool way of running in Docker. So it will fire up a bunch of Docker containers inside Docker containers inside Docker containers. It's all containers. And we'll immediately, yeah, you can see that it brings up 3 nodes. I don't know if you actually can see that. It will bring up 3 nodes, and all of those nodes are Docker containers, and it will set up the Kubernetes context to this kind cluster after it's done. So what I'm running now is a setup which will basically load all of the services in using the YAML definitions that are in that I'll show you in a minute. And that's not very big. Maybe that's better. And you can see that it's creating the MySQL container, and it set up a bunch of things for the kind cluster to work. Set up the kubeproxy, set up DNS handling and all that jazz. A control plane, yeah, core DNS. Now, the reason I should have started this earlier is that it takes a long time to pull down the images because they're quite large. Yeah, it's pulling MySQL. All right. And while it's doing that, oops. You know, NSQ is coming up. Do I have network? Yeah, I have network. Yeah. So these are. I've gone with a. Every service is in a single repository kind of thingy, just to keep track of them better. So I have my kube files. I have a bunch of. I have a couple of secrets which sets up the MySQL username and password. I have NSQ lookup, which sets up the service and the deployment for NSQ lookup, and the NSQD, which is the stateful set. And this is where the service discovery comes in check. It basically defines the NSQD lookup address in the address environment property and sets up the NSQ daemon to look for that lookup service. And I also have like a small front end. MySQL is there, cool. This is really slow. I also have like a small front end to look at the images that will be redeemed, and this is the kind setup. So basically, what I'm doing is I have 2 workers, 1 control plane, and the extra mounts are used instead of the PVC because of that kind because I need to mount in my local storage in order for them to be access the images that we'll create. All right, face recognition is coming up. Receiver is done. Okay, almost there. And so, talk about a little bit of a structure of a service. So, as I was learning Go, one of the most important things that came along. I come from a very long development in Java world, and it was like a breeze switching over to Go, and really easy to use. But one of the first things I kind of had to relearn or unlearn rather is how we do dependency injection or dependencies and testable small modules. So what I chose to do is have this provider-based architecture. So for example, you have a service or you have a functionality that you would like to provide. So you basically write an interface for that, which is like a consume. It consumes things, the processor processes things, and the storage stores things. And I'm using Go generate with counterfeit to generate a fake out of that, out of these interfaces in order to be more, to have them be more testable. So I have a consumer which implements this interface, implements the consume. It's really trivial. It just sends things to, gets things from the queue and sends it to a processing, sends it to a channel basically to be processed. It adds a handler to the queue, NSQ stuff that will be called whenever there is a new image ID that is received. The send to channel is then being consumed by the processor, who will process those in a continuous for loop. So you can, if you can see that, that's here, all that is here. This is basically the brain. If there's a new ID incoming, then it will process that. And this is running, should be running in a Go routine. Let's see how that stuff is. Yeah, face recognition. So this is like a larger container because it contains dlib and stuff like that. So it's like 800 megabytes. Hopefully that will load fast. But now we have the front end running here. So currently there are no persons of interest. But we can, so if we look in known images or known people, we know two people. Robert is my brother, and I know myself somewhat. And we have a couple of unknown people. I don't know how much that can be seen, like a couple of unknown people. 1, 2, 3, 4. One of those is me. One of them is my brother. The rest is who knows. Should have started that. And so when there's like a curl call to how currently this service is accessed is it's being port forwarded out of the Kubernetes through the service that is running. Oh yeah, it's up. Oh, okay, I can actually show something. And we basically send a path in that there is a new unknown person, and we have a record in the MySQL database belonging to these people. So if we select from people, use cube. People images, person images, no. Person images. You can see there are preloaded records. Basically, this is done in a setup. We have like person 1, person 2, person 3, person 4. Person 4 is me, and my brother does not exist. We have a bunch of other people and John Doe. And so if I do a curl call, we see that there's a pending image, a new pending person incoming, for which we don't know who that is yet. And after a minute or so, NSQ kicks in, and we will see that the image processor eventually picks up that there's a new thing in the queue. The first one, you can see the errors because the queue and the channel doesn't exist yet. But every minute it will do a lookup, and after it exists, it'd be a lot faster. So once it gets to the point where it actually picks up there you go, and got the person, and it should be Gergely. Whew. Nice. All right, and just so you know, I'm not cheating. Oh, where are all these things? This is me. And just so you know that I'm still not cheating and it's not hard-coded. Hang on. Oh, did I kill that? Yes. We could do a thing with a photo booth. And then and then save that into known people. No, that's unknown people. Yeah, okay. Unknown, whatever, 05. And then unknown 05. Oh, I really hope this works. I mean, I am smiling, so that might throw it off. But let's see. Anyways, unknown people 5, right? Yes. And it's Gergely. Yeah. All right. That's it. Yeah. So that's really cool about this. And that's it, basically. Thank you. Thanks for listening. Thank you. I think I've gone really. Are there any questions?
Do you want to do questions?
No, I don't.
Do you want to do them?
It's really difficult.
You insulted me earlier, so I'll make the decision for you. Any questions based on that? Wow, what a great and creepy talk that was. Good stuff. Thank you very much. Okay, well, we have a little break now. In fact, and I think 4:15. 4:15. How do you say 4:15 in German?
In German, I'm Hungarian.
Okay. It's finally happened, everybody.
Aber ich weiß ein bisschen German, also.
That's because I googled your name to try and learn how to pronounce it, and it's.
Brautigam is actually German. That is true. My father is German.
Yes. In a way, I feel like somehow that makes it okay, and I'm not going to be cancelled.